I'm Hernán Tacca from University of Buenos Aires. I will propose a method for core loss estimation in switching converter design for power electronics application where waveforms are not sinus waves. This is the presentation outline. First, the kind of losses are introduced and the classical statement equation valid for sine wave operation is presented. Then the statement equation is extended to consider non-sinusoidal operation, and later a mathematical model is proposed to take account of DC magnetizing bias influence that increase the core losses. Finally, examples of application in typical converters are presented. The core losses are usually classified in three kinds of power losses. First, the eddy current losses, which are produced by eddy current circulating through the core material. Second, the hysteresis losses are due to the non-reversible trajectory of the induction when forced to perform a closed repetitive cycle. Finally, some losses that cannot be included in the above two categories were named as anomalous or excess losses. The total core losses density will be the sum of the each contribution, and the resulting core loss will be computed multiplying the total loss density by the core volume. As this equation has too many parameters, a simplified expression, now as statement equation, was introduced to calculate the total core losses. This equation has only three parameters which depend on the material features. These parameters may be determined by curve fitting using the experimental data from loss measurements. Actually, they are not constant over the entire range of frequency and induction operation, so they should be obtained from manufacturer curves using data close to the point of converter operation. However, some mathematical models were proposed in the reference to predict these variations. Several prediction models were proposed based on modification of the classical statement equation in order to take account of arbitrary waveforms. A way to consider the effects of non-sinusoidal waveforms is to include the derivative of the induction into the expression of the instantaneous power losses, since these losses will be null during the time intervals where the induction is constant. The first proposal was named natural statement extension and has a parameter Kn which must be numerically computed in order to obtain one graph or a table to allow an easy application. The second generalization done to consider non-sinusoidal waveform was named modified statement equation. There, an equivalent frequency is defined in order to take account of the influence of the derivative of the induction in polyharmonic operation. This equivalent frequency is easier to calculate than the previous parameter Kn. Also, the frequency of the waveform fundamental component must be considered. In order to consider the influence of the minor loops, another generalization was proposed at Dartmouth College by Professor Sullivan and his research group. This expression requires to make some numerical calculation, and a software to take account of minor loops effects is complementary available. However, if minor loops are not present, an approximative formula may be used to compute the proportional parameter. To achieve equation that can express the core losses preferably as a function of the electrical variables of the converter circuit, rather than as a function of magnetic quantities, a modification of the mathematical model called extended statement equation was proposed. A new empirical parameter epsilon to be measured has been introduced, but it could be expressed as a function of the classical statement parameters with acceptable accuracy. The optimum value for the parameter epsilon must be determined looking for the best fit with experimental data. However, a good match was found adopting an equation that is only function of alpha. Dividing the power loss density given by the extended statement equation by the power density expression corresponding to the classical statement equation, one obtains an adimensional multiplier factor that may be useful to compute the actual losses in non-sinusoidal operation as function of quantities obtained using the original statement equation, valid only for sine wave operation. So this multiplier could be also used to obtain the actual losses, correcting the loss values given directly by the power loss curves for sinusoidal waveforms issued by the core manufacturers. For unipolar waveforms, expressing the voltage shape factor as function of the induction and substituting it in the preceding equation, an expression of the extended statement equation is obtained as function of the shape factor of the applied voltage. Notice that to obtain this equation, no assumptions were made neither on the type of converter nor in its waveform, except for the unipolar waveform feature required. Also, to consider the minor loops power loss contribution, a Simulink program was developed similarly as it was done for the improved general statement equation. In this case, the average transformer voltage is a low-frequency sine wave, and the duty cycle is the time-dependent function required to produce the sinusoidal average value. The effective voltage applied to the transformer is given by the second equation, and the average rectified value is given by the third equation. For typical values, the multiplier factor is almost equal to 1. Therefore, the datasheet curves for sinusoidal waveform could be applied for power loss estimation. In the figure, one may see that the output current has a ripple which introduces minor loops into the main fundamental hysteresis loop, thus increasing the core losses with respect to the previous case where unipolar modulation was used. As a consequence, the major loop will have losses increased with respect to the case of sinusoidal driving according to a factor given by this equation. For main frequency and typical core values, the core losses may be increased 15% with regards to the case without minor loops. That is the former unipolar PWM inverter. Therefore, the total multiplier factor will be the former multiplier factor increased by 15%. So, in order to keep the core losses equal to the one expected for sinusoidal waveforms, the maximum induction allowed should be reduced 10%. Let's consider the chopper circuit presented in the first figure on the left. It is actually a half-bridge circuit performing as a buck chopper, assuming a very big output capacitor and continuous operating mode. The waveforms become the ones presented in the second figure at right. The magnetic core will have a DC magnetizing bias produced by the average output current. From the waveform figure, the rectified average expression of the induction derivative, the induction effective derivative, and the voltage form factor are derived. Substituting in the expression of the multiplier of the extended statement equation introduced in a previous slide, equation number 1, the final equation presented here is obtained. Notice that this multiplier will take account only the loss increase due to the asymmetry of the waveform. An empirical model based on experimental measure is proposed given a multiplier factor to multiply the modified statement equations in order to estimate the increment of losses due to the DC magnetizing bias. The proposed multiplier factor is a function of the DC bias induction, the peak-to-peak value of the AC induction, and 3 empirical parameters which depend of the magnetic material considered. Experimental measures show that nu has not a critical value. Also, with some lack of accuracy, the parameter C may be expressed as function of kappa. Now the application to a flyback converter operating in continuous mode will be analyzed. Again, as it was found for the half-bridge chopper, a DC magnetizing bias is present. Notice that now it's possible to adopt a transform radio suitable for operating with the duty cycle close to the optimum value to avoid the core losses increment due to the waveform asymmetry. In continuous mode, the output voltage is a function of duty cycle, the input voltage, and the turns ratio. And the voltage shape factor is just a function of the duty cycle. Defining the transistor profit factor as the ratio between the output power and the maximum apparent switching power, one obtains the expression of the profit factor as a function of the duty cycle and the normalized current ripple. The optimum duty cycle is the one maximizing the profit factor of the transistor. Finally, adopting the optimal duty cycle, the extended statement equation multiplier shown in the expression below is obtained. By the Ampere law, it is possible to express the magnetic quantities required by the mathematical model formerly proposed to take account of the DC magnetizing bias to obtain the additional core losses. Substituting in the multiplier formula, one obtains the expression here presented. For transformers for PWM symmetrical converters made with laminated steel, only a core loss increment of 15% should be expected regarding a classic transformer operating with sinusoidal voltage waveform. For symmetrical high-frequency switching converters, the classical statement equation or the manufacturer course measured using sinusoidal waveform may be used as a core loss estimation accurate enough for practical first prototype design. For those symmetric converters operating with asymmetric waveforms and superimposed DC magnetizing bias, both loss multiplying factor proposed in this work should be used. For asymmetrical converters, one of the modified statement equation must be applied when the duty cycle is far off the optimum value, and some prediction of the core loss increment due to the magnetizing bias should be made when the DC bias is comparable to the magnitude of the alternating induction. In most asymmetrical converter topologies, with duty cycle near 50%, the experimental curves for sinusoidal operation will be accurate enough for loss estimation, but the DC bias influence must be considered. Thank you for watching.